Welcome back. How's everybody doing today?
Good.
This is like week 4, something like that. So, yeah, we're ready to move on. I've got a couple announcements like I normally begin class. First, no office hours today. Been saying that. Sorry to be repetitive, but I realize I need to be. The second is you have a formative assessment out. It won't take you very long. 4 questions. Not tied to Lisa's, but similar content. I heard about it, yeah. But basically, she writes down everything anyone ever says and gives me the transcript when she gets home. That's not true, but we do talk whenever there's points of overlap. And it is convenient that this class and her class are going at the same time. But anyway, you have a formative assessment in here. I try to give you one every week, so just use the cadence of it. It's due before noon on Friday, not p.m., a.m. Yes?
What's the content for the...
Anything I talk about in class or things that were part of what we need to. Yeah.
Okay.
Yeah, it won't be what we're doing this week. It'll be from the week before. It helps me understand what you're getting from lecture and what may or may not be coming through. So, thank you. And also helps you understand, if you struggle with these questions, they're usually the very high level, like the big picture points. So anyway, any questions for me about class or anything that we're doing? I'm sorry about the homework. I planned on doing it this week, and then I'd start building my lecture for this week. I hadn't built it yet. Built it this weekend. I know. Fun times, right? And I'm like, yeah, how am I going to give you a homework without teaching you about Stan? Because you're going to be using Stan in your homework. And then I'm like, well, that's going to cut into homework time. So I decided just to push it a week. So, okay. Next week, it'll be a homework. It'll be using Stan. It'll be like regression. So, all right. Other questions? Okay. Now, this week, so let's think here. First week in a couple weeks were what is Bayes? And then there was what is psychometrics? So we had like Bayes lecture, we had psychometrics lecture. Guess where we're going now? Back to Bayes. So what you'll see today in class will not look psychometric unless you remember that psychometric models are effectively linear models. We just collected all the data this time. Okay? Sound good? So when you see a regression, by the way, try not to think this doesn't apply to this class. Try to think this is a building block that I need to do the bigger analysis, because the bigger analysis will be a bunch of regressions, the psychometric analyses. I think I made that point last week, right? Okay. I have our studio. I've got the lecture slides down at the bottom here, and I'm going to move those. Can you all see this okay? Great. So today, the lecture that I put it on there is Markov, Chain, Monte Carlo, and Stan. I'm just trying to teach you the basics of MCMC and the basics of Stan to use them for MCMC. I'm not diving into what does it mean yet or how does it work yet. It'll just be how to get it working. Like what's underneath the hood will be magic still. I'd like to get to that later. In looking through the previous iteration of this class, I started with, let's build MCMC from like what's under the hood, and I don't think that went as well. I'd like you to understand it, see a concept of it first, and then we'll talk about why that happens, okay? So an introduction to MC, introduction to Stan. I say both with linear models. There's a really stupid linear model in here, an empty model. I say it's stupid. It's a beginning model. But in the style of Professor Hoffman, I plan to have an example that does the linear models with Stan and MCMC for next week. So we get through all these slides this week. It may take us a while, and then next week we go into that. I encourage you, let's see, do I have it up? I encourage you, if you'd like, to actually follow along with the files from this lecture. If you download this zip folder right here, you can grab that and start running Stan while we're doing this. So you can try it yourself, see how that works. Is your question? No, gotcha. Okay. Hello, everybody online. Good to not see you today. Something like that. Is that what you say when you see people on? Good to not see you? Good to see you on my screen? I don't know. Good to see you on my screen. That sounds more polite. I don't know. All right. So, in the style of so I've learned a little bit about YouTube in the last few years because my kid loves it now. And I thought, oh, I could be like Mark Rober here. Be like, this is a posterior distribution. You may wonder how we got it, and I'm going to teach you today. How's that sound? Like, hit you with what's up? Huh? My YouTube skills are lacking. But let's start with that. That is a plot. It's called a time series, a Markov chain time series. There's actually two parameters to it. There's one on this side, one on that side. What do they look like to you? If you were to describe that plot with words, this is a Bayesian Rorschach test.
Looks random.
Random. I like that.
A mess.
A mess. I like that too.
Is that uniform?
It's not uniform.
Alpha side.
What's that?
Alpha side.
I'm sorry.
Alpha side.
Yeah. It's very. I don't know. Anybody? I've heard people call these caterpillar plots because if they're done right, they look like little fuzzy caterpillars. I don't know. I see people haunting me. No, never mind. Rorschach, right? Sorry. Okay. No, what we're going to talk about today is getting these, how they come, how we assess them, where we go with them. Yeah.
What are the units on the axes?
Good question. That's a mystery.
Mm.
On the y-axis, it's the value of the parameter. On the x-axis, it's the iteration where that parameter was sampled. So literally what's happening in a Markov chain is that every iteration, all of the parameters of the model get a value somehow. Now that somehow will remain a mystery until we get further into what's underneath the hood. But this is how a Markov chain looks, if it's done correctly. So, yeah.
How many iterations do you normally do?
It depends. Sorry, I don't have a good answer for that. I'd say whatever it takes. 220, 221, never mind, sorry. Mr. Mom, old movie. Never mind. Whatever it takes. We have some criteria by which we assess the Markov chain that I'm going to talk about in this lecture. And if the Markov chain is not assessed to be converged, then we run more. But figuring out what that first level is takes practice and an understanding of how much data you have versus how much model complexity there is. This model has two parameters. It's effectively a mean and a variance, or mean and standard deviation. I could probably run 100. I wouldn't want to do that. I could have run that much and gotten a good chance of seeing it. But we'll see why I'm holding off on that is you're going to see what goes into how we evaluate this and why we need to run it long. Okay?
Great, thank you.
You're welcome. So, shall we? Let's go into it. This is a different picture of the same chain. On this, there's actually 4 chains here. You can't really see very well with the colors, but they're overlaying each other. So I ran 4 separate Markov chains. And then, at the end of it, there's 10,000 iterations. So each chain ran 10,000, or actually ran longer than 10,000 iterations, but we had it sample 10,000 iterations. So now we've got, if you count 4 chains times 10,000 iterations each, we've got 40,000 data points per side of this plot. If we took those data points and forgot about when they occurred in the sequence and just compiled them into a distribution, these are posterior distributions. These are posterior distributions formed from the Markov chain itself. And I'm going to talk about how you get those too. But basically, hold on one second. Remember, in Bayesian statistics, our goal is figuring out the posterior distribution. We are using the Markov chain to literally etch a sketch of that distribution. These are densities that have been smoothed, like little histograms to do. Yes?
So I have a couple questions. The first, so is this the confidence interval, but just mapped out visually?
This is the entire posterior distribution.
Oh. So we get the whole thing.
We see the whole thing.
Wow. My second question, I think you might have answered this already, but how does this differ from bootstrapping, we're not estimating parameter values, but is it kind of the same idea?
So bootstrapping is doing the same, usually maximum likelihood based analysis with differing data at every point. The differing data is constructed by resampling the original data. So every time you do an analysis, say you have 100 observations, you do this same empty model, mean or intercept and standard deviation, right? Every time you do that analysis, you get a new mean standard deviation, but the data has changed. Whereas here, what the heck just happened? For us, we have the same data. What we're doing is we're specifying that we have a model likelihood, we have some prior likelihood, and we are literally trying to find the posterior with one constant set of data under our model likelihood and prior likelihood. Okay? So the difference is quite a bit, right? In bootstrapping, why do we change the data? Because we think there might be influential observations. Here, they may be there. We won't know about them. This is sampling a posterior distribution. Hope that answers your question.
Yeah.
Okay. Other questions? So, what do you think of those posterior distributions? Kind of ugly. I mean, if you look at it, can you see my cursor? Yeah. It's kind of, I don't know, there's a little wiggle to it. This one's a little skewed. There's a bump here. They're never perfect. They're never all the way smooth like you'd normally see a distribution. That's because the process by which we're doing this is sampling. And depending on how long we run our number of iterations, it may be the case that we just, through quirk of our sampling process, got a little bit more mass of a probability here than what a smooth distribution might look like to be. So this is, you remember the kid's toy, the Etch-a-Sketch? You ever seen that before? Mm-hmm. For those of you who haven't, if it's got sketch in the title, you know it's going to be kind of iffy. But it's like this. There's little wheels, and there's a little point that draws. That's us. That's a Markov chain. It's trying to draw the shape of a distribution, but it's not really smooth. All right? All right. So that's my best Mark Rober. Now let's get boring. Bayesian analysis is all about trying to provide estimates of the posterior distribution. And that is literally it. That is our posterior distribution. The distribution of beta 0 or the distribution of sigma conditional on our data. Now, up until this point, well, we only saw one posterior distribution. It was something we knew, right? We assumed we had that dice roll example where I took a die and I said that was Bernoulli, and I said, oh, the probability it follows something beta, and through the magic of a conjugate prior, I know the result is a beta distribution, right? So I can figure out what that distribution looks like. However, beta and beta, there we go. Like conjugate priors don't always happen. In fact, they're not needed. You don't need a conjugate prior to do Bayesian analysis. There's an exponential family of distributions. If you're familiar with that, listen to what I'm saying. If not, just hold off. Don't worry about it. But there's for a large group of distributions you can show, I don't know why it keeps moving, but for a large group of distributions you can show that there's several choices of prior that are conjugate, but you don't necessarily need a conjugate prior. Conjugate priors, not a big deal, okay? It sounds good, but it's not a big deal. Why? Okay. But most of the time, posterior distributions aren't really easy to get. They take a lot of effort. So because of that, we can't just say, oh, I know the posterior is beta distributed, sample it, figure out a beta distribution's mean and call that my posterior estimate. Right.
I have a question.
Yeah, absolutely.
So on the previous slides, you were showing the chain and then the distribution. Those were two parameters. When you're talking about like the posterior distribution, like this is for every variable that you would potentially.
That's right.
Model.
That's right.
Okay.
You can think of, we could have plotted these in 2 dimensions. We could have done like a contour plot of the parameters, but quickly we lose sight of what that means. So a posterior distribution, each parameter itself will probably have, will have a posterior distribution, and that's usually how it's summarized, is that this one parameter, here's its univariate posterior distribution. Does that make sense?
Say it again.
Yeah. So even though this model had 2 parameters,
Yes.
what I'm showing you on each side of this is a parameter by itself. That's what we call a univariate distribution. That's the most typical way we display it. Now with 2 parameters in a model, why is it doing that? It's going to kill me.
I think I'm doing it somehow.
Did I give control?
I don't know how, but I'm pressing the. Okay, well, I'll just close out.
Wow. What the heck?
That is weird. Sorry.
No, it's okay. Come on, Nathan, quit hacking my computer. Were you in Teams?
No, I just went to the site, like from the site.
No, this should be a local. Try it again.
Okay, hold on. Okay. Oh,
I'm not
that's
touching
not
it.
doing it.
Okay, I'm not
Maybe
touching
It's
it.
just coincidental, but
I'm not touching it. No. Is anybody on Teams doing this? Do you have control? Weird. Anyway, I've lost my train of thought. So, point being, we could, with just 2 parameters in a model, there's lots of ways of displaying this plot, which is, we could think we put the density for beta 0 on one axis, the density for sigma on the other, and we have a contour. But we don't usually use that. We usually look at each parameter by itself
Okay.
in analysis.
So right now we're looking at the posterior distribution of our predictors.
Of our parameters,
Parameters.
model parameters. That's right. Yes, that's right. So we haven't told you what the model is yet, but we're going to work up to that. That's part of the mystery. What's that intro in YouTube to get those? I need to get you past that critical point of viewership, right? Is anybody a content creator on YouTube here? Just thought I'd ask. If you are, let me know. I need your tips. Never mind. So, long story short, the first lecture we did on Bayes, I said, oh, there's a posterior. Turns out it's beta distributed. That whole phrase quickly does not apply to most analyses in Bayesian, right? Because what we will do is, oh, there's a posterior. I have no idea what distribution it follows, is what we're after. So we use Markov chains to figure out what the distribution is. And we use those chains to give us our parameter estimates, things that we like to call credible intervals, which are the Bayesian version of confidence intervals, and so forth. The story of our data. How we doing? Alfonso, every time I see your drink there, I'm like, that's a Budweiser. Like out of the corner of my eye. And then I start to think, while I'm talking, that'd be pretty cool if we were all drinking beer while I'm teaching. It's not a Bud. For those of you who are witnessing this, it's not a Budweiser. But now I want one, even if Budweiser's terrible. Anyway. All right. Sorry. Ah, what's going on?
Oh, I know it. So I rendered it in R, and it must have connected somehow.
No, it shouldn't connect. This is all local.
See, yeah, I don't know. That's weird.
Try it again.
Okay. Yeah?
And you're not signed into Teams.
No, I'm doing it through our studio.
That's weird.
Yeah.
All right, well.
In previous classes, it was the opposite. I was watching it on the website, and whenever you change a slide, it would change it in my computer without me doing anything. But I was on the website, not on R.
Weird.
But
I am.
the last class and this class, it has nothing.
Okay, we'll see. All right, you know what I'm gonna do? Let's go over here. I'll just grab this right here. See if this works better. There we go. All right, so it turns out this brute force sampling that we just saw a picture of, that I haven't even told you about why or how, if all we were after was the mean of those posterior distributions, we wouldn't necessarily have to do the brute force sampling, right? We could actually use what we call an optimization algorithm. Optimization meaning trying to find a maximum. That's an optimal point of a likelihood. In this case, it's not a likelihood, it's a posterior distribution, but we can calculate what the posterior is, we can figure out where its peak happens to be. So I want to mention that even though today is about Markov chain Monte Carlo, don't say that all Bayesian analyses are Markov chain Monte Carlo, because you can do Bayes without this. You can optimize something. Those problems, though, sometimes take a very long time to run. So sometimes, for what I call high-dimensional problems, what's a dimension? If we're doing multidimensional IRT model and have 6 traits, the Bayesian optimization version will take just as long as the ML optimization version, which may never converge in your lifetime. Well, that's not true. It may take longer than you have to do an analysis. So at some point, the Markov chain actually becomes more efficient, but it all depends on your setup. So, but what we're trying to do today is sketch, make a rough sketch of that posterior distribution. Right? We are sampling from it. Now that's cool. How can we sample from something that we don't know what it is? That might be your question. The answer is magic. It's math. It's theory, and it's sort of some theoretical properties that make it happen. So you have to take my word for it that this is happening today, because a lot of this class, I mean, I could dive into the math behind it. I don't know that you need it or that I need it, but we could just appreciate it for what it is. Does that sound good? Do you want theorems and proofs? And no, some of you do. There's a stat department for that. I'll just go with how it works. I'll also talk a little bit about the algorithms when we get later on in class. Uh-oh. Jihong says, Quarto includes a built-in version of the Reveal Multiplex plugin. It allows your audience to follow the slides of presentation you're controlling on your own phone or laptop. Oh, I see. So somehow it is trying to share with you my slides, but anyway, that's kind of cool. Weird, but cool. All right, so the sketch and the sampling that's happening is done with this Markov chain, right? It's not as easy. So we're simulating data effectively. Have you simulated data before? No. Well, you're in luck. Some of you have, many of you have, but that's okay if you haven't, because not everybody needs this skill. But I'm going to show you right now. I can simulate data like this. If I do hist, the R norm function is random normal. And if I do 100 values, there's a sample from a normal distribution. I can't do that for MCMC because I sampled directly from a normal. A normal is not our posterior distribution. Our posterior distribution depends on data. So the process of MCMC and what the complicating factors and why there's multiple algorithms for it is how we go about sampling values from things we do know that end up representing the thing that we don't, which is the posterior distribution. And we do so through this progressive sampling approach. Next week, well, maybe not next week, at some point in the future, when I get into the algorithms, I'll talk about what we're sampling from as we go build it. And that will lead me to talk about why things converge to the posterior under most normal cases where you'd use it under some mild assumptions. But for now, we'll have to rely on it being magic. Can I say that in this class? It's magic. All right.
It's Disney magic.
What?
Disney magic.
Disney magic? I thought you said density magic. And I'm like, that's exactly what it is. It's density magic. We're going to have a, I don't even know what we're going to have. I was going to go down with Disney there for a little bit, but then I should just stop. I was going to say like the Tinkerbell of MCMC. Never mind, we could go places there. That's an old reference. What's a newer? I don't know.
Encanto. Magical.
I haven't watched that one. No, sorry. All right, so what do we do with MCMC? They iteratively sample from the posterior distribution. What does iteratively mean? It means one iteration, we are actually sampling each parameter value itself. Right, so every possible parameter in our model has a chance to take a new value. Yes.
No, just keep talking.
Okay. So that part of it is the Markov process, where at each point, or each iteration in the chain, each value has a chance to change to something brand new. And then the next iteration, it's not the current, it's a brand new value from the last chain, it has a chance to switch to another value, and so on, and so on, and so on. Question now? Or-
So hypothetically, if we had like a beta 1, a beta 0, beta 1, beta 2, each chain is like, we're going to use this value for beta 1, beta 2, beta 3. Like,
Yes.
here's this value, and then we're going to do it again.
That's right. That's right. So we actually start off with a random guess. Now, that random guess has to have some properties to it. Our parameters need to be within their sample space, right? We can't, if we have a probability that goes between 0 and 1, we can't say it's 3, right? We have to put a value there. But we start off with a random guess, and our sampling is very bad. We're most likely very far from the density that we're after, which is the posterior density for each parameter. So we take a new guess, and that new guess will move us slightly closer. But we'll keep doing this over and over again. And each parameter in the model will start to move toward the density, the posterior density, the thing that we just plotted as we're sampling. So it's an odd perspective. How are we doing? It's weird, right? There's so many questions. How? Why? For now, just know it happens. I know it's hard to suspend belief, right? For fairly simplistic model, we can think that each iteration has independent samples, but most models have some layers of dependency. What do I mean by that? We can't sample theta simultaneous to sampling the item parameters in an IRT model. However, the thetas are person parameters. We need to sample them. So we do that as one iteration in the first part of an iteration. And then conditional on those new thetas, we'll go and sample the new item parameters as another part. But all of that's the same iteration because we have to go through every parameter within an iteration to allow it to change. Does that sound good so far? So the more complex models you get, as you imagine, because every parameter has to have a chance to change its value in every iteration, the more model parameters you add, the more complex, the longer things take to run. And what's happening with respect to what we're calling convergence, convergence is when a Markov chain reaches the posterior distribution. Like we converge to this posterior distribution and we sample from it. Each parameter is moving at a different rate toward their posterior distribution, but they all have to kind of go there to get there together. So some may get there quickly, but others may take a while to get to theirs. So this whole thing, the more complex our model gets, the longer the chains have to take to run, because each iteration, each parameter sort of needs to have a chance to move. Are we okay with that? All right.
I'm feeling better about the magic.
The magic. That's what I'm going to call it for now. It's just magic. It's math. All right, it's math. It's actually mathemagic. Oh, that's a dad joke. That's bad. Can we strike that? I'll have to go back to my...
There's actually a movie called Mathemagic. I don't know that.
I mean, I know you're a math person, and I like to claim to be a math person, but I can't go there. So if I can go back and scrub that from the video, I probably should, but I guess I won't. So that's one of those edits I really need to make, and I don't have the time to be a YouTuber, so I'll just be a professor. So it turns out there's actually a number of these MC-MC algorithms. Most of these algorithms use one of two types of sampling. Direct sampling from the posterior. So if you can come up with the posterior distribution or a family shape of it, like we did in our first example, we could still sample from that. That sampling is called Gibbs sampling. It's direct sampling, which means I know the posterior is this. I'm going to sample from it. Now, you might ask, why would we need to sample from it if we know what the posterior is? Because we might know what it is up to a set of parameters, but we don't know what those parameter values need to be. So for instance, in a linear regression, you have what Lisa would call the model for the means. your fixed effects, your coefficient, your regression coefficients, you have your residual variance. You can't sample, you can sample the regression coefficients, but they have to be conditional on what the residual variance happens to be. Likewise, you can sample your residual variance, but you need the regression coefficients to sample it. So even though you could write down what the full posterior would be, you still have to do this iteratively to sample one because the other depends on that value. Right? You might say, I will draw the residual variance, and then I will draw the regression coefficients, and I'll iterate between the two. And that's the need to have this iterative Gibbs sampling approach, even if you can specify what the posterior distribution should look like. It's an odd thing to think about, but it's there. The other, okay, again, most often this is conjugate prior land, because you need to be able to write down what the posterior is. The other version of sampling is something we call indirect sampling, or rejection-based sampling, which is, I don't know what the posterior is what you sort of say. Where am I going with this? I'm pretending I'm the algorithm? All right. Let's say you don't know what the posterior is, but you can form the posterior based on Bayes' theorem. Right? You can show sort of it's proportional to the data likelihood, the prior likelihood. If you add in another proportionality factor, you can then sample from a distribution that you know how to sample from. But that sampling would be to propose new values. So basically, in our linear regression example, and this is actually what's happening in Stan, we have beta 0. At each step in the chain, Stan has a part that suggests the new value of beta 0. Right? If it was at 10 before, the new part may say, hey, try 11. And then, based on the likelihoods, we form a probability. And then based on that probability, we either stay where we're at or we move over. Right? We either accept or reject the proposed value of the parameter. That's why we call this a rejection sampling approach. Types of algorithms that are called rejection sampling include Metropolis Hastings. And what Stan uses, which is Hamiltonian Monte Carlo, turns out Hamiltonian is a type of Metropolis Hastings. And for those of you keeping score, the Metropolis algorithm, I think that's 1953 was when that was published. Right? It came into statistics widespread in the 1990s. So like you can think about how knowledge disseminates and forth. I think it came from chemistry, if I'm not mistaken, for where it came. Then newer approaches such as Hamiltonian, it's called Hamiltonian because it depends on Hamiltonian dynamics and physics, which I'm, not my expertise, but it tries to come up with even better versions of suggested new parameters, proposed values, and that's why it is nice. It's efficient, is what we say. Questions? How's the pace of this? I'm sort of dragging this out because there's a lot to remember in each of these things. So efficiency is the main reason for many of these algorithms. What is efficiency measured by?
Wait.
Yep.
So you just named other algorithms. Do they all fall under the umbrella of MCMC?
They do.
They do.
They do. Gibbs sampling, Metropolis Hastings, Hamiltonian Monte Carlo are all MCMC algorithms. And then there's variants in each that are flavored like that. Good question. Other questions? Okay. Efficiency. You can think of efficiency this way. How quickly do we get to the posterior distribution? Right? Now, quick is with regard to how fast your sampling goes from somewhere way outside where the density is to the center of the density of the posterior. If I were to go back to, this is dangerous, I'm going to try it. Sorry for those of you, whoa, that's not what I wanted to do. For those of you following along on here, if this is these are our densities here, goodness, come on. You could think we might start off with a value way out over here and then progressively work our way bouncing around toward the center. Right? And an efficient algorithm is how quickly we go from where we start to the center. But there's another added feature of efficiency, which is effectively how correlated our successive draws happen to be. So when we sample each parameter, if we were to go and look at a time series correlation, so what is a time series correlation? You can think of it this way. There are 10,000 observations on one of the sides of this. If I took the 10,000, I think of that as a big column of data, and I moved and I made a copy of it, and I pasted it one row off. So that now that I've got 10,000 observations in one column and 10,001 in the next column with a missing spot in the first, if we were to correlate those two columns, that would be called an autocorrelation. An autocorrelation of a lag 1. Right? If we moved it off by 10, it would be a lag of 10. And so one of the things that we're looking for in a Markov chain algorithm to talk about how fast it goes is how correlated our parameter draws are from successive iterations. We actually do calculate a chain autocorrelation, we call that, as part of our way of considering whether the chain has converged or not. I saw a hand. Yes?
I, of course, have a question. So if the idea with these algorithms are that they're going to converge on a particular value or to the center, would that show up on this sort of time series graph?
Yes. Now this is a time series graph that doesn't show the full story. Because in the Markov chain algorithm, there's a period that shows up before this, called the burn-in, or warm-up, where it's sampling, but we know it's not in the center, so we're going to disregard it. So we don't show it here, but I'm going to show that later on as we go. So I'll come back to that.
This is more like at the end it's converged.
This is at the end. When we see this output from Stan, when we plot it, we're very happy. Why is that? We don't see a trend. What's happening in this picture, if you were to pretend you are one iteration at a time, you could imagine us being here at one point, and then switching over here at one point, and then switching over here at one point, at random, bouncing around the inside of the mass of that density. That's what we want it to do. We want it to be in the middle, bouncing around at either side of that density to give us a good shape for it. Right? We want to sample
So
it.
almost like a funnel.
That's right.
Okay.
Yes.
So should the other plot get like thinner as time goes by?
Well, to a point, but we have to remember the density itself will have variance to it. So we're not just after the peak of the density. If we were after the peak, it would certainly get thinner as we get closer and closer. What we're after is the full shape. So what will happen with this plot is, and again, I'll show this in a few slides. So I may be a little bit ahead of myself, but there'll be more of a story filling in. If we were to plot the other observations, you'd see it not wiggling as much, but slowly moving up. And then when it gets to where the close to the center is, that middle of that distribution, why you're seeing it up and down but no trend to it is it's literally bouncing around where the center of the density happens to be. And that's a really good thing for us, because remember, our goal is to sketch out the density. So we want it to wiggle around, but we don't want it to have a trend in its wiggle, right? We don't want it to be up for 50 and then down for 50 and whatnot, right? We just like this big seismograph, whatever. Did I answer your question? Awesome. Other questions? Okay. Make sure I'm not missing anything. Okay.
Oh,
Yeah.
clarification for the note page.
Yes.
What did you call the front end of?
A burn-in. I'll be right
Burn
back.
in.
Burn-in, but we're going to have that coming up, so hold off for just a moment. It's coming. But anyway, efficiency is how quickly it can sketch that algorithm itself, quickly being the number of iterations it takes. No one algorithm is uniformly most efficient for all models. And here I'm saying a model is the likelihood times the prior, the posterior distribution that we're at. Some combinations of model likelihoods and prior likelihoods give you easy things to work with, some don't. And that's why all of these algorithms show up. The good news is you don't have to pick the algorithm. Right? It's built into a package. Right? In fact, it's trying to help you not pick it. Stan itself has Hamiltonian. It has some of the optimization things as well. JAGs, M+, you're specifying the model. The software is trying to figure out what's the best way to go and give you the result. So you don't actually have to learn that. Although I want you to learn a little bit more of it because I'd love to show you how it works. When you see it, like if you compare how hard it is, at least in my head, how hard it was to learn maximum likelihood, you're going to go, this is MC, this is it? Like, yeah, this is it. Like it's model likelihood, prior likelihood, and in the rejection sampling, then there's a likelihood of transition, like the proposal density. Anyway. And bad news is, sometimes your model may take a large amount of time to reach convergence. Okay? So it may take days. I've had it take weeks. But hopefully, for what we do in this class, it will only take minutes. And hopefully very few minutes. But it is complicated. It's doing a lot of computation. So, now if you really want to make this work, if you really want to scale this up, that's where you get to build your custom algorithm yourself. What does that mean? You write it in your own code, write it in a fast computer language, put it to work in a very small problem or a typical use case. That's how it works. My dissertation, I developed a Gibbs sampling algorithm for diagnostic models. I coded it myself in Fortran. Yes, that Fortran. And it went pretty quickly for that problem. It wouldn't do anything else but it went pretty quickly for that. So that was nice. Then ETS, which I was working for as a grad student through a ETS contract to Illinois, decided they wanted to patent that. So they patented my dissertation, which is weird, but that's there. Yeah, I'm an inventor, a listed inventor on like 2 patents. So anyway, how are we doing? All right. There are a lot of commonalities across the algorithms. And actually, the nice thing about it, so what I'm saying, introduction to MCMC, but not diving into the algorithms, is the things we're going to talk about here apply regardless of which algorithm you choose to use. Whether it's, and even then, you don't even know which algorithm, you don't have to know which algorithm. The average Bayes user says, I used M+, estimator equals Bayes, or I went and threw things in Stan, right? Well, why Stan exists because it used that newer version of an algorithm, but most of the time we don't think about it. But the way that we look at the data that goes in, the way we decide our settings, and the way we establish convergence applies regardless of the algorithm. It's all the same. So, number one, the first thing is we need a period of the Markov chain where the sampling is not directly from the center of the posterior, right? This burn-in period that we have to go through. Right? We don't know what the posterior distribution is. We don't know where the center is. So we don't know where to start our algorithm. So as a first iteration, the starting values are drawn at random, typically from a prior distribution or from a range of values that we specify on input. Those starting values are likely to be very discrepant from the posterior. So we need this burn-in period to figure out, to sort of get to the center of the posterior. And then we collect, and after that period's over, then we're like, all right, now we'll let it bounce around, literally bouncing around from side to side at that shape of distribution, and we'll record those sampling iterations. So the big term that we use is burn in, which is sort of the idea that we start the algorithm somewhere far off. Now there are a few algorithm-specific versions of tuning that happen. What I mean by tuning is if you're in a rejection sampling algorithm, right? It's the algorithm that proposes values from a simple distribution that then accepts or rejects based on where you're at in the chain. Those proposed values sometimes need a little bit of help. So we use, what do I mean by that? We can very quickly start off with an algorithm that says, I'm going to generate random proposed values from a normal distribution with a variance of 100. But then quickly need to know that that would be way too big for most. Like we'll quickly propose values that are far outside where we need them to be and likely to be rejected, so they're inefficient. So what we end up doing it's sort of tapped into the burn-in is that we sort of update parts of the algorithm too. We say, oh, it looks like the posterior distribution's variance is much smaller than 100, so let's move our proposal variance smaller. That's one way of looking at it. There are other techniques for tuning as well, more complicated, that you get when in different places. Stan just calls everything a warm-up, that you can see other versions of this wherever you go. In fact, I don't use SAS for this in the class, but there's actually a proc MC, and they do a great job describing what they do in their chains to sort of get the chain ready to estimate. It uses Metropolis Hastings to do things, but I actually cite their user guide here in just a moment. So, thoughts or questions so far? So burn-in, what's a burn-in period?
Calibrating.
It's the part of the chain that we don't keep. It's our goal to make the chain efficient and close to the center of the posterior. That's what burn-in is for. Okay? And we don't even record those values. We're just like, yeah, run. We'll start counting after 10,000 iterations, or we'll start counting after 1,000 iterations, or something along those lines. That's the big picture of burn-in.
Do you specify that?
You can.
But you could let the software just be like, run your burn-in, and then once you can just chain, go.
Most of the software will try to automatically figure it out for you. Now that's not a good idea in a lot of what we do. So my code, it will be specified. But if you pull up M+, and you say estimator equals Bayes, it will not ask for it. Same thing with SAS, same thing with Stan, actually. It'll just default to something. The default is probably not necessarily one size fits all.
Is there a way for you to know what to specify before you run it? Or is it like you run it and you're like, oh shoot, we got a little bit of a fan going at the beginning, we need to rerun it?
It's the latter. It's run it, check it. If it didn't work, change the specs, rerun it. Yeah. Well, that's the problem. We don't know the shape of the posterior distribution, and the only way we would know using these algorithms is to try.
No, it makes complete sense, and I can see it being a little devastating if you just spent weeks running this and then...
Well, the practical part of it, the art of it, is knowing how to set things up and to test so you don't get in that trap, right? So if something is running and you know it's going to take a long time, test it where it's not going to take a long time and see how that goes. Like test it, check it. Most of the time the burn-in is, for most of what we will be working on, this is not a problem. For the models in this class, for the typical psychometric models that we do in this class, things will work very nicely. Surprisingly nicely. In fact, I just demonstrated something with a Markov chain that I would never advise anyone doing, but I needed to demo this yesterday afternoon. And I did a Markov chain for 200 total iterations, 100 burn-in. Didn't converge, but it got the point across, and you could totally see it starting to converge. I would never want that few, because again, if we're after the shape of a density, this thing right wherever it went, if we're after that shape, you can imagine 100 observations isn't going to make it very smooth, so we're not going to be accurate.
Is there any sort of indication within these softwares of how, is estimating how long it's?
Yes.
Okay.
Yeah. In Stan, we're going to see that. It'll actually tell you right when it starts running. This first thing took however many seconds for this many jumps. Adjust your timing accordingly. But not everyone will. So, yeah.
I have two questions. First, when we are using these algorithms, we are including all the parameters we are interested in at the same time.
That's correct.
So this burning period, do we have to include all the parameters?
Yes.
Or can we set?
That's right. Yeah, the whole thing has to be the same as it would be for the sampling. And so all the parameters need to burn in for the whole period. Yeah.
So at the end, when we're going to explore these plots,
Mm-hmm.
they are individual plots for each parameter, but the algorithms consider all the parameters in order to
That's right.
work.
Yeah, that's exactly it. If you think about it, at every step of the chain, there's some dependency. Some parameters need other ones to be fixed to be able to draw them from. And from each iteration, there's a dependency on the previous. There's an autocorrelation of some sort. But at the end of it, we sort of look at the parameters separately. But we have to remember that dependency that we're getting from the Markov chain is actually a dependency we'd see in other likelihoods as well. If you think about a multivariate likelihood, I know that's a weird thing to think about, but think of it this way. If we weren't doing MC-MC, we will be trying to figure out, let's see if I can do this. This may be too much information, but I'm going to say it anyway. Let's imagine we have a three-dimensional graph here. And let's imagine we have beta 0 and sigma squared here. These are the two parameters you showed on your graph. Somewhere there will be a density, a multivariate density, that we're sampling from. But that density is likely to not be where each of these dimensions is independent. There's some dependency that shows up there on it. We don't know what it is. So we're dealing with that dependency as well too. The dependencies show up based on how we form a model. That's what we're after. Did that answer your question?
Yeah.
Probably went too far. Oversharing. All right. Other thoughts, questions? So the first thing, again, all of these algorithms I talk about have some period of burn-in. I'm going to call it burn-in. You may see warm-up and stand. The second commonality is the way that we assess whether the algorithm converged is the same. How do we know we converge to a posterior distribution? That's nice, because that means I can teach this lecture without saying, you know, I'm using Stan, yes, but this is better than us being specific to Gibbs for one way or Metropolis for another. Most of these methods used to assess the convergence of the chain actually would prefer that you run multiple chains to get your estimates. We'll see why in just a bit. So but think of it this way. I said there's one Markov chain. The plot I had 10,000 iterations of sampled. There was another, actually, bless you, 10,000 sampled for burn-in before that I didn't show you. That's one. But for that analysis, we did it 4 times. And those multiple chains help us assess whether we converge to the same location. There are, when you get into really heavy-duty Bayes, I'm going to call it that, some really crazy combinations of models and priors and stuff. What you're worried about, what keeps people who do this up at night, is you'll start to converge to a posterior distribution, but you'll be converging in potentially a mode of a posterior. What's a mode? A local region of a posterior. There might be another region somewhere else, and if we start our chains with different random values, we try to rule out the case that we might have another region that we're sampling in. Right? If our posterior distribution looked like this, right? Depending on where we sample, we may only get this picture, or we may only get this picture. But if we do multiple chains, we might get the full picture of where that posterior looks. And that's part of the reason for multiple chains. We want to make sure that we're converging to the same spot when we randomly start in different places. Now, that sounds scary, but for the reality is, for most of the stuff we'll do in this class, there's one very distinct mode. There's actually more than one mode, but okay, I'll say it. Remember the psychometric models? I'll just say it out loud. You can have theta be positive and your factor loadings be positive. Right? That's what we normally want to see. But the likelihood's equivalent if theta is negative and the loadings are negative, because the negatives cancel. And that's what I talk about with another mode altogether. Now that mode is not something we worry about because we can easily tell that that happens. But when we get to more and more complex models, most of which won't apply in our class, you may need to worry about that. Okay? It'll look a lot, I feel like I'm scaring you. MC's terrible, but I use it all anyway. Now I feel like if I had to do it, you did too. Back in my day, we did MC in the snow with no shoes on, and we liked it. No? Finally, how we summarize a posterior distribution is the same. Once we get that plot of the distribution, we do the same thing with it. We check its convergence the same way, we talk about its results the same way. So it's really nice. It's just getting that plot of the posterior distribution is the difficult part. All right, we did talk about tuning. There we go. Questions? Yes?
Can you go back to that picture with the binomial?
Yeah. This thing.
So I'm just wondering with converging, because you want to keep running it so that it converges, but then you want to do it multiple times because it can converge in a couple different ways.
That's right.
And that is because you're using the prior each time, and so it's like I'm trying to wrap my head around why it wouldn't be giving. You wouldn't see like a jump or something with it would converge only over here, only over here. Is it because it uses that prior?
It's less than that. It's sort of when we tune a distribution, particularly if we're doing rejection sampling, this proposed value, right? We might have a value that's currently right here in the chain, but we might propose a value somewhere in that area. Now how it actually picks things is if the value is further out, it may reject it. If it's further in, it may accept it, right? But you may never get so far out such that the peak of this distribution gets close to you, right? But it still may be there because of the way that the likelihood function gets built. So diagnostic models and finite mixture models have likelihood functions that may not have one peak. And that's scary, not only here in Bayes' world, but also in maximum likelihood world as well too. If you go to M+ and you say, I want a mixture model, by default, it starts at 10 different times, runs at 10 different times up to 10 iterations, and picks the one that has the highest, or the highest likelihood, and finishes it with that last one. And it tries to figure out whether that likelihood would be repeated itself. So we worry about this in multiple places, but what ends up happening likelihood-wise is typically when you start to get close to one, you can't get out of it. You sort of get sucked into that mode. And having a multiple chain, we're hoping that you get sucked into a different mode if it's there.
So it's more because of that acceptance versus rejection that's going on?
It's the way the algorithm is tuned. You may not be able to break out of the regime that you're in.
Okay.
It would take a lot of a chance happening that probably wouldn't occur during the span that you're sampling from.
So how many iterations would you think of doing to make sure that you are catching all of those?
That's a great question. I don't know. It depends on how complex the model is. If you're doing certain classes of models, like anything mixture model based, you may consider more because of that. But for most of the things we do in this class, they're almost certain to have a single peak unless you pick a really bad prior. And at that point, we probably won't have to worry about it at all.
So when you're talking about CDMs, they have all of those different.
They potentially do, yeah. Yeah, there's multiple modes in mixture models. It may be the case that the 3-parameter logistic model has multiple modes in IRT. It doesn't fall under the exponential family. We're getting too far ahead of us. Yes?
Do each one of the chains start at a different burn-in?
They start at a different location initially. All of the parameters are randomly started somewhere initially.
Okay. But they're different.
Different, yes. And that's the key. If we start in a different place, like if we had started where this one parameter was here, it's most likely going to move to that side. But if we had started it over here, it may never see that side because it gets in here. Stuck. How are we doing? Yeah.
What's the role of the data in this context? Because we're trying to calculate the posterior, but what can we do with the data likelihood?
The data likelihood is driving the posterior. It'll probably be the biggest influence on the posterior, depending on how much your sample is. Is that what you're asking?
No.
No, I'm sorry.
But because in this context, I can understand that we are trying to predict some values sampling from the posterior, yeah?
Mm-hmm.
But what what is the role of the data in this context? The
Oh.
observed data.
Oh, they're part of the data likelihood. So so what you're doing remember in Bayes, your posterior, let's say the likelihood of a parameter given the data is proportional to the likelihood of the data given the parameter times the prior likelihood of the parameter. Because the data are right, that didn't work out. Because the data are right here, they're locked in. They're part of that data, that model likelihood. And so because of that, like last time we talked about a normal distribution, and I say normally we pick a mean, we pick a variance, we plug in the data. In this case, it's the opposite. We fix the data there, but each time we try a new mean out, we're trying a different height that's coming from it, conditional on that data. Does that answer?
Yes.
Great. Thank you for rephrasing. Anything else? Okay. All right. To demonstrate each type of algorithm, that's not true. To demonstrate what we're going to show here, I'm going to use a model for a normal distribution. So here's the data I'm grabbing. Post-diet weights. And these aren't my data. I grabbed them from UCLA. Here's all I have based on the diets. 30 subjects who use one of 3 diets. Diet 1, Diet 2, and a control group, which is Diet 3. Before the start of the study, the height of each subject was measured, and after the study, the weight of each subject was measured. I have no other details than that, but weights and outcome. That's all I have. Okay? As someone who's struggled with his weight most of my life, this is normal for me in my lifetime, but yeah, it's sort of sketchy. Whoa, I didn't want to do that. All right. Let's just do this. Here we go. Okay, 30 respondents. The variables, I have respondent, I have diet group, I have the height in inches, and the weight in pounds. And that weight in pounds is what I'm going to be modeling today. And then the example I'm going to build, which I haven't built yet, will have the whole thing, and that'll come hopefully next week. Okay? So, there are research questions. Are there differences in the final weights between the 3 diet groups? And if so, what are the natures of those differences? You saw the example data didn't have those questions, so I'm imputing them. And like anything you impute, caution is needed. But I'm pretty sure these data are simulated anyway, so we'll just pretend. We're good at pretending, right? That's what posterior distributions are. They're all make-believe. Not true. Let's look at the data first. Hey, look at those data. That's our dependent variable. What do you think of that? How's that look to you?
Looks like the case that we just went over, like with the 2.
It does, doesn't it? Wow, that's a crazy distribution. And there's our height variable. And oh, hey, that's height and weight by group. Or height by weight by group. Excuse me, weight by group. So you can see the different pictures there. Diet group 3, that was our control. They have more weight. And here's some pictures of our plot. The height in inches versus the weight as colored by the diet group. And this is why I think these data are simulated. There's not a whole lot of overlap here with diet group 3. So, probably simulated. So let's do this. I want to do Bayes, but I also want to teach you statistics. And you've done linear models, and you know this. Let's go through this. What type of analysis seems most appropriate for these data? ANCOVA. Yes, analysis of covariance. The next question. Is the dependent variable, weight in pounds, appropriate as is for such analyses, or do we need to transform it? Do you want to see the picture again? That. What do we assume? ANCOVA is a linear model. What do we assume about the outcome in a linear model? What?
It's unbounded, continuous.
Unbounded and continuous, correct. What's its distribution?
No.
Normal. Possibly. Not normal.
It's more like supermarket.
But
I know, sorry.
there was a modifier to normal.
Conditionally normal.
Conditionally normal. What does conditionally normal mean?
Conditional on a particular value.
Conditional on the predictors, the distribution is normal. So you use the predictors to form a conditional mean, and the conditional mean then says the rest is normal. So how can we tell if this is conditionally normal? We can't. But I can tell you if you transform it, that's not a good idea. Because it doesn't need to be normal. So just remember that when you look at data. And you start to say, oh, this isn't normal, I need to transform it. Don't transform your data. It's a bad idea usually. That's my sidebar conversation.
Was that like in your vows between you and Lisa? Like,
It was. It was. It was there.
I will never transform.
Thou shalt not. No, it's if any of you have me on your PhD committee, the last question I ask is, have you transformed data lately? If your answer is yes, fail! Just kidding. Just kidding. I'm not that strict about it, but here, let's play with some models, shall we? I actually started with an empty model, and I thought this is a good chance for us to all practice some ANOVA. Not that I really want to, but you know, maybe you do. So, oops, that's not it. I have an R file here that has all these data in it. And I stopped at the linear model. Does anyone want to help me build what the model should be? I just have an empty model right now. This is the empty model. It has an estimate of 171 for the intercept and a standard error of 49.52. What is this intercept also equal to, since this model has no predictors?
You know what I mean?
The mean, that's right. So if I did mean, diet data, weight, it's 171. What is the residual standard error when there are no predictors? The standard deviation. Very good. So I can't trick you all. 49.52 or thereabouts. Pretty good, right? So that's what we expect. But if we were to build this model, let's leave that for the next time. Let's stay empty right now. The next one will be all about model building, all right? So staying empty, I can still talk about stuff. There's a path model. I'll get to that next time too. All right, so what are the steps? We've got these data. We just talked about Markov chains. What are we doing? We want to build a Bayes analysis. And so we're going to go through the steps of a Bayes analysis using MCMC. Here are the steps. Number 1, specify your model. For us, we're staying empty right now, which means our model, remember what a model is, what I had told you before? It's not just what the predictors are, or what the linear component is, it's also the distribution. Right? So we're saying y follows a normal distribution with a mean beta 0 and a standard deviation sigma. That's what we're saying with this. Second, we specify prior distributions for all the model parameters. So we need to know what are the model parameters. Beta 0, sigma. We just talked about that, right? Third, we need to build the model syntax as needed. So this is where we grab Stan and start building syntax, and that's what we're starting to do. Fourth, we run the Markov chains. We have to specify a warm-up or burn-in and the sampling period lengths to do so. We then evaluate chain convergence, and then if it has converged, we report the results. I needed a flow chart, because really if it hadn't converged, we might rerun these with longer chains, or we might change prior distributions in how we build these. But at the end, once we have convergence, we evaluate or interpret or report the results of the analysis. Sound good? So this is this similar to what you're used to with analyses or no? I mean, you have to specify a model even if you're like, well, I have an ANCOVA. Well, that's implied a model, right? That implies a few things. You clearly don't need prior distributions. You do need model syntax. Although if you're doing things by hand, I would question whether that's reproducible. Sorry. Maybe it is. Show your work. Anyway, instead of running Markov chains, you run your analysis. You may have to evaluate convergence. Maximum likelihood algorithms, iterative ones, may have to converge. Right? So you still have to do that, and then you report and interpret results. So in some ways it's the same, and that one key step about the Markov chains is very different. Okay, so here's our model. Weight in pounds is equal to an intercept plus a residual error, where the error term follows a normal distribution with sigma squared error. What are the variables in this analysis? That would be like the nodes in the path diagram. How many variables do we have? Just one.
So error is not.
By variable, I mean observed and data likelihood specific variable. What goes into the data likelihood is really what I'm trying to say. There's one, and it's weight in pounds. What are the parameters in this analysis? Now, that's where you might say. Two parameters. Right? We actually have beta 0. And even though we specify error here, really, once we have beta 0, it's trivial to figure out what error is. Right? Just subtract beta 0 from this and get error, right? But in the specification of error, there's the sigma squared error. So the two parameters are beta 0 and sigma squared error. So why we have to enumerate that is because when we're building our syntax, we need to give those parameters prior distributions. Now, I'm going to say right now, if you don't put priors in Stan, it'll run. But please don't do that. Because it will run with a uniform prior across the sample for those. So I want you to remember the prior because it's in almost every other Bayesian piece of software you'll need it. Okay, 2 minutes, 3 minutes. Let's talk about Stan real quick. Stan is an MCMC estimation program. Technically, it can do optimization too. It can do likelihood-based stuff. I've never used it for it. It also has something called variational Bayes, which is a likelihood-based estimator, somewhat newer than Hamiltonian Monte Carlo, but I've never used it for it either. It is the most recent large-scale program that I know of that's out there, and it's much more convenient than some of the older ones. Back in the old days, there was bugs, Bayesian updating by Gibbs sampling was the acronym, bugs. It used Gibbs sampling. It was really hard to get to work. Then came JAGS, just another Gibbs sampler, another acronym. It used Metropolis, or Gibbs sampling. It used several different algorithms, Gibbs and Metropolis. But again, it was a little clunkier. Stan is much nicer. Starting values are easier to pick. There's been a lot more development money put into it, and it's still open source at least. So it's very nice. It has come a long way in the last 4 or 5 years, actually. It's become super great. You create a model using Stan's syntax. So here's the difference. Stan is not in R. Stan is a standalone program, right, by itself. So you install Stan, even if you use R and you like library or install packages RStan, it's installing Stan for you, but you didn't have to do that. You could download it and install it directly onto your machine without R for it. But then it has its own syntax system. But here's the cool thing about Stan. It takes your version of Stan syntax and translates that into C++ code that you don't even see. Right? C++ is a high-level programming language, works very fast. So it built a custom-built executable of the algorithm that runs just your model. Right? So it has this compiler, or it needs, to run things. This is where installing Stan may have caused some hiccups in your system because it may not have the right tools it needed to take Stan syntax, write it into C++, and compile it. But I'm out of time, so I talked too slow. We'll talk more about Stan when I come back. So for now, thank you. Thank you for being here online. Thank you for being here in person. I have a couple minutes for questions, but I gotta go. I got a meeting at 2. So anyway, good to see you. Hope to see you Friday. Thank you. Thanks to everybody. Just 1 second.